All right, so this is problem 19. It says use the modified form of Kepler's third law to calculate the orbital period in days. All right, so the first thing is, what do we want to know? We want to know the period. Period equals question mark in days. All right, so that's an A, sorry. And they give us the name of the star, or an exoplanet. They give us the mass of the exoplanet. This is actually considered what they call a super Earth. Anytime it's like 2 times the mass of Earth, all the way up to about 10 times the mass of Earth. That's considered a super Earth. Anyhow, that really doesn't have anything to do with this problem. The star, they tell us the name of the star. Now this part is important. The star has a mass of basically 31% the mass of our sun, or 0.31 times the mass of our sun. All right, so let me write that down. All right, so the mass of this star, which is called Gliese 8851. Not that matters at all. All right, so the mass is equal to 0.31 times the mass of the sun, of our sun. And the mass of the sun is really well known, right? That's on the problem sheet, the formula sheet. All right, and so the value of the mass of the sun turns out to be 2 times 10 to the 30th. All right, so here we go. It's going to be 0.31 times 2 times 10 to the 30th kilograms. All right, so we let's see if we can quickly do that. This is not very difficult. All right, so with this calculator. All right, anyhow, here, actually, you know what? I'm just going to use a different calculator because it does everything in scientific notation. Unfortunately, you can't see. All right, so anyhow, you just say 0.31 times 2 times 10 to the 30th. All right, so that turns out to be 6.2. So this is what we're going to use. All right, so the mass is 6.2 times 10 to the 29th kilograms. All right, so now how are we going to use that? It says to use the modified version of Kepler's third law. Now, if you look on the formula sheet, there is an equation for the period, right, where the period is equal to the square root of basically the p and the mass switch places, and then of course you have to take the square root. So anyhow, it's the square root of 4 pi squared times the distance cubed divided by big G and divided by the mass of whatever you're orbiting. So in this case, the mass is going to be this number right here. Now, the other thing is the D. The D here has to be in, here, let me just point to it. D has to be in meters, right? In meters. All right, and so when you do this, and by the way, the period, of course, comes out in seconds. Right, so we gotta do some conversion to get it into days, but that's pretty easy. So the one thing that we have here is that the semi-major axis is 0.22 astronomical units. So what that tells me is D is going to equal 0.22 AU. And so you just have to know how many meters there are in 1 AU. If you look on the formula sheet, it turns out that there's 1.5 times 10 to the 11th meters. Right? Usually I write it as 150 million kilometers, but we want it to be in meters here. That's 1 AU. All right, and then of course the AUs cancel. All right, so this turns out to be, I'm going to keep this in scientific notation here. Here, let me get my calculator. There we go. All right, so it's going to be 0.22 times 1.5 times 10 to the 11th. And that's, of course, meters. All right, so it turns out to be 3.3. So this is going to be 3.3 times 10 to the 10 to the 10th meters. All right, so now we're ready to solve for P. All right, so P is going to equal. So now you're just going to put the numbers in. So it's 4 pi squared. Let me pause this. All right, so I paused it just to write this all out. All right, so these are all the numbers here. All right, so I'm going to do this in my calculator, and we'll see what the answer is. Remember, the answer P here, so this is what P is going to come out in seconds, and then we'll convert it in just a moment. All right, so when you put all these numbers in here and you take the square root, you get this number right here, which is, what is this, 5,857,226.471 seconds. And then, of course, there are 60 seconds in a minute, 60 minutes in an hour, and of course, 24 hours in a day. All right, so we take this number, we divide it by 60 squared, and then we divide that by 24. All right, and that'll give us the answer. Okay, so when I do this, I get 67.79 over, and they tell us to, what does it say? Round to one place past the decimal. All right, so the answer would be 67 point, what did I have? 79. So it would be 67.8. Right, that's a decimal point. Days. All right, 67.8 days. All right, so that is problem number 19. All right, and this is problem 20. Let me just write that here, 20. All right, so the last one was 19. All right, so for this one, it says estimate what percentage of the sun's light is blocked mid-transit by computing the ratio of the area of the Earth's disk and the sun's disk, and estimate what percentage of the sun's light is blocked. It was part B, sorry, but by Jupiter. All right, so each time here's what we're doing. Okay, so it's actually a really basic idea, right? So if this is the sun, and then let's say this is a planet, as the planet passes in front of its star, and this is, by the way, is what's called the transit method. It's going to block some of the light. All right, so we're going to, we're assuming that it's a sphere, and so the surface area of any sphere is pi r squared. All right, so we're going to use the pi r squared. So in the first one, it's the radius of the sun. I'm sorry, we start with the Earth. Pi, of course, the pi's are going to go away in just a second. So it's going to be the pi's disappear, and so it's just the ratio of the radius of the Earth divided by the radius of the sun, and then you square that ratio, or you can square the numbers first. It doesn't really matter. It's the same thing. All right, and so notice right above this we have the radius of all the different objects in. So this is actually going to be part A. All right, so for part A, we're going to use the Earth. All right, so it's going to be 6378. All right, so notice this is in kilometers, and then just to let you know, so you like I said, you can square this first, or you can square the ratio afterwards. It doesn't really matter. The sun is huge, right? The sun is the biggest object in the solar system. Anyhow, it's 6.96 times 10 to the 5th kilometers. All right. And then of course you're squaring that. So the kilometer part cancels. Oops, I forgot to put the square. All right, and so this is going to be the pure number, and then what you're going to do is we got to turn it into a percentage, and so that then we multiply that number by 100. All right, so we're gonna get some number, and we're gonna turn some. Yeah. Anyhow, here let's do this. All right, so this one. Let me get this. There we go. So it's just 6, 3, 7, 8. You could, like I said, you could square it first, or you could so 6. I mean, you got to do one or the other, right? If I'm going to square the first thing, if I'm going to square the numerator first, then I divide by the denominator squared. All right, so divided by 6.96 times 10 to the 5th, also squared. All right, so this is going to, so it's an incredibly small number. It's like I get 8.397, anyhow. So something like this, something like 8.4 times 10 to the minus 5th. So E minus 5. All right, and then of course what you do is to put it on 100, you multiply by 100, right, to get it into a percentage, right? And so this becomes, and the decimal just goes back 2 places, right? And so, all right, so this becomes here, so times 100. All right, so it becomes 0.00. I mean, it depends on where you want to round this. 8. I rounded it to. Well, let's see. What did I say? Did I say how much to round it? Anyhow, it's like 3.39. All right, 7. All right, so I'm going to round it to 2 places past the decimal. So it's going to. And by the way, this is of course because we multiplied it by 100. This is the percentage. So it's 0.0084%. So only 0.0084% of the sun's light is blocked. All right, as we're going to see for Jupiter, which is much larger, it's going to be a lot more of the sun's light, comparatively. All right, so it's going to be 7.1. Here, let me pause this. All right, so to estimate, this is part B, estimate the percentage of the sunlight that Jupiter blocks mid-transit. So when Jupiter is, going across the sun from some distant vantage point, how much of its light, and again, you do the same thing. It's just the ratio of the radius of Jupiter in this case divided by the radius of the sun. And again, you could square these individually, or you could just square the ratio. Absolutely doesn't matter. At any rate, when you do this, you get 0.01046, and it goes on. And then of course, remember we have to get it into a percentage, so we multiply this times 100%. Right, so we multiply it times 100, right? So times 100 is going to give us times 100 is just going to move the decimal place 2 places to the right, so it becomes 1. And it's like 1.05. 1.05 if we rounded 2 places past the decimal. But remember, because we multiplied by 100, multiplied by 100, this is now a percentage. So with Jupiter going across the sun, a little more than 1% of the sunlight is blocked. All right, just to let you know, these transits that we see to look at exoplanets is usually much smaller than 1%. All right, so because they're usually not going directly across. There's just they're crossing just part of the star.